Okay, so now we've got our second merge talk at the conference. This is the double act of Joschka and Oscar, talking about bias-tailored quantum LDPC codes and how fragile boundaries limit performance of surface codes for biased noise.
Okay, so thank you. Right, in the first part of this merge talk, I'll be discussing bias-tailored quantum LDPC codes. This is work done in collaboration with Larry Cohen from Sydney, Amanda Kindervale from Sheffield, Darius Chandler for 1QBit, and Earl from River Lane. Okay, so often in quantum computing theory, we like to think of qubit decoherence in terms of a Pauli noise model. Where we assume each qubit is subject to a Pauli error with probability P, where P is the sum of bit flip errors, phase flip errors, and wide flip errors. Okay, so perhaps the simplest manifestation of this error model is the polarizing noise, which corresponds to a uniform contraction of the Bloch sphere as a qubit decoheres. So this is a nice toy model to study qubits in theory. However, once we start looking at qubits in practice, we find that they're often subject to some sort of asymmetric noise. So cat co-qubits, for example, typically have phase noise that dominates by several orders of magnitude. So instead of getting a nice uniform contraction of the Bloch sphere, we get an asymmetric decoherence. And the question that I'll be attempting to answer in this talk is how we can take advantage of this asymmetric noise to improve the performance of quantum error correction. Okay, so we had a very nice introduction to the standard surface code in the previous talk. There you have two types of stabilizer check. One type of stabilizer check that detects bit flips, and another type of stabilizer that checks phase flips. So the reason we got interested in bias-tailored codes was as a result of a numerical study of a bias-tailored form of the service code called the XZX code by Bonilla et al. Last year. And the way that the XZX code differs from standard service codes is instead of having two types of stabilizer, we only have one type of stabilizer. And this stabilizer can detect both bit flips and phase flips simultaneously. And similarly to the service code, we can construct instances of this code by tallying together copies of the stabilizer to form a surface. So this looks very much like the standard service code, and indeed for depolarizing noise, the threshold of this code is exactly the same, so bounded by 19%. However, the performance of the two codes begins to differ once we start considering bias noise. So in particular, if we look at the extreme case of infinite X bias, in this regime, the performance of the XZX code depends exclusively upon the edges that detect X errors. So we get rid of the blue edges in our XZX codes, and this gives us what we call an X-checked subcode, which we see is just a set of independent repetition codes. And the repetition code has a threshold of 50%. So what this means is that in going from depolarizing noise to infinite bias noise, the threshold of the XZX code increases from 19% to 50%. So this is in stark contrast to the standard surface code where the threshold actually decreases as we go from depolarizing noise to infinite bias. And we see a similar thing when we consider infinite Z bias, just the repetition codes now act in the other orientation. Okay, so Bonilla et al. Were the first to study this code numerically, and what they found was that the XZX code actually outperforms the standard surface code for all Pauli noise models where there's some sort of noise asymmetry. And to illustrate this point further, here's a plot from our paper where we compare a standard toric code against an XZX version of the toric codes for different bias. So bias is on the x-axis there, logical error rate on the y. The blue line is the standard toric code. We see that the logical error rate gets worse as the bias is increased, whereas it's exponentially suppressed for the XZX codes. So we see that just this small change in the stabilizers makes a huge difference in terms of the practical decoding performance in the bias noise setting. Okay, so yeah, the overall question that we wanted to answer in this talk was, given that we can increase the performance so drastically with the surface code and creating the XZX code, can we do a similar thing for more general families of quantum codes? And the specific families of quantum codes that we're interested in are quantum low density parity check codes. These differ from topological codes such as the surface code in that they have the ability to encode multiple logical qubits per logical block. So the service code, for example, only encodes a single logical qubit. So the ability to encode multiple logical qubits in a single block opens up the possibility of much more resource-efficient quantum error correction. And there is some spatial results in the past year have shown that such quantum LDPC codes with finite rate can exist with block length and distance scaling that vastly outperforms the surface codes and is comparable to the best known classical LDPC codes. So from this, the takeaway is that quantum LDPC codes are great. However, there is some fine print, and that is that in going from topological codes to quantum LDPC codes, we lose the locality that we have with the surface codes. So here's an example of a quantum LDPC code that encodes 16 logical qubits in 80 qubits in total. And as you can see, the connectivity is complete spaghetti. So it's unlikely that we'll be able to easily implement something like this on, say, the current generation of superconducting qubit devices. However, as we saw in the opening talk yesterday, there are architectures in development that promise beyond nearest neighbor connectivity. So perhaps something like that could be a good test bed for codes, quantum LDPC codes. Okay, so how do we go about constructing quantum LDPC codes? Well, in the previous slide, we saw that we can construct a topological code like the XZX code simply by tiling together copies of a fundamental stabilizer building block. And we can create large instances of that code by creating bigger surfaces. In quantum LDPC codes, however, these are based on random constructions, so we can't rely upon that repeating structure. So what we instead have to do is we have to use a so-called product construction. And the essential idea behind this is that it's a recipe that takes two classical codes defined by parameter matrices H1 and H2 and combines them in a special way to create a quantum code with commuting stabilizers, commuting X and Z stabilizers. So to go into that in a little more detail, a famous example of a quantum product construction is the hypergraph product. This takes two classical codes, H1 and H2, and then combines them as follows to create a set of X stabilizers, that's HX, and a set of Z stabilizers, H delta. And we can construct any quantum LDPC code simply by taking the hypergraph product of two classical LDPC codes. Okay, and we're in fact not limited to just quantum LDPC codes with this construction. In fact, we can also create topological codes. So, for example, the repetition code, the hypergraph product of the repetition code gives us the surface code. So given that we can get the surface code from the hypergraph product of two repetition codes, we set out to see whether we can also get the XZX code from two repetition codes via a similar product construction. And what we realized is that the surface code actually only differs from the XZX code by a Hadamard on a subset of the qubits, specifically the qubits that act vertically. What this corresponds to in terms of the hypergraph product code equation is swapping blocks 2 and 4 in that matrix. And this gives us a bias-tailored hypergraph product that can be used to create quantum LDPC codes that respond well in the bias noise regime. Okay, so once we've created this bias-tailored quantum hypergraph product, the question was, which classical code should we use to construct these quantum LDPC codes? And the family of codes that we eventually settled on were classical quasi-cyclic codes. These find widespread usage in classical communication technologies such as 5G and Wi-Fi. And a specific advantage of using classical quasi-cyclic codes is that they can be directly repurposed into quantum codes via a modified form of the hypergraph product called the lifted product. And the lifted product is a recent innovation in quantum product constructions and was late last year used to derive one of the first proof of good quantum LDPC codes in the asymptotic limit by Pantelevin Palshev. Okay, so to give you some sort of idea of the benefits of using one of these lifted products over this conventional hypergraph product, let's look at the sorts of codes we get when we turn a classical code with parameters 52 through 26 into a quantum code. So if we use a standard hypergraph product code, the resulting code has length 5,408, whereas if we use a lifted product, we get a code of length 416. So you see, for this particular example, we get a 13 times contraction in the block length. Okay, so as with any quantum codes, a bias-tailored quantum LDPC code is only useful if we can efficiently decode it. So unfortunately, we can't use the minimum weight perfect matching decoders that work well for topological codes because the syndromes of quantum LDBC codes don't have the correct type. However, what we found is that a belief propagation based decoder augmented with order statistics decoding works extremely well. There's not time to go into this in detail today. However, we have open source our implementation of this decoder that you can also install via pip. And there's an example of how you can go from importing this decoder to doing some decoding within 10 lines of code. So feel free to try it out if you're interested. Okay, so here's a part of some of our numerical results where we decoded a bias-tailored quantum LDBC code using BPOSD. So on the x-axis, we have the x bias, which is the ratio of the x error probability to the other error types. On the y-axis, we have the word error rate, which you can think of as the logical error rate per logical qubit. And if we look at the purple line at the top, we see that as we go from depolarizing noise on the far left and ramp up the bias, the logical error rate is exponentially suppressed before plateauing off. So we see that we get an improvement, and the plateauing corresponds to the point at which the quantum code, the logical error rate of the quantum code, then corresponds to the classical quasi-cyclic code upon which is based. And we see that we get similar behavior for all other values of the total error rate between 6 and 10% that we considered. Okay, so I alluded earlier to the fact that quantum LDBC codes might be more difficult to implement than topological codes. So why should we use them? And to quantify this, we compared the bias-tailored quantum LDBC code that we constructed with a topological code, so in this case, the ZZX toric code, and put them on the same plot. So the quantum LDBC code we're considering is the same one from the last slide, and the blue line is the toric code. And if you go over to the far left, you see that they have approximately the same word error rate. So you might be asking, what exactly are we gaining? What this plot doesn't tell us is the fact that the quantum LDBC code encodes 18 logical Qs of bits, whilst the toric code only encodes 2. So what we actually find is that in going from our topological codes to our quantum LDBC code, we're reducing the overheads by approximately a factor of 12. Okay, so that's the end of my talk. So in conclusion, you can use bias tailoring to improve the performance of quantum codes in the bias noise setting. You can use our bias tailored forms of the hypergraph product or the lifted product to create such codes, and they can be decoded using BPOSD. So this was a very quick introduction. If you're interested in learning about it in more detail, we have a detailed tutorial on our repository, and you can also download our paper.
Might be heavy in the mic. Okay, so in this part of the talk, I'll be talking about fragile boundaries of tailored surface codes. And this is joint work with Tom, Alex, Steve, and Earl, and the archive can be found there. So as with Joschka's part of the talk, we're also interested in bias noise, as for example, in the AWS Capco qubit architecture. And as already mentioned, the square CSS surface code is not optimal for bias noise. And so what we focused on is, given a planar 2D architecture, how can we tailor it to the high bias? Now, one way of doing this is just a simple modification of the CSS surface code, which is just a rectangular CSS surface code. And here the idea is you reduce the x distance relative to the z distance of the code by changing the aspect ratio. And that way, and you do it such that you approximately equalize the x and the z logical error rate. And by doing that, you save a factor of log eta, where eta is the ratio of z to x errors in qubit overhead below threshold. And then you take the limit of the x distance being 1, you just obtain the repetition code, so you can use that in infinite bias, and it has weight 2 checks, so it's easier to implement in the surface code. So you can think of that as the thing to beat for infinite bias. The XY surface code is another modification of the surface code, another way to handle high bias, where you replace the Z stabilizers with Y stabilizers. And this has a 50% threshold at infinite Z bias. And that's because it has an area like Z-type logical. So if you apply the only Z-type logical is if you apply Z error to every single data unit. And it's been shown that it has high thresholds under a sort of phenomenological noise model, as well as in co-capacity simulations. But prior work does not consider circuit level noise, and it also doesn't consider logical state preparation and measurement, and lattice surgery. And the disadvantage is you can't optimize the lattice dimensions for the bias, because the aspect ratios give the X and the Y distance, but not the Z distance, so you can't tune to the bias. So in this work, we introduce belief matching and belief line, which is decoders that use belief propagation to handle correlated circuit level noise and surface codes. Using belief matching, we compare the rectangular CSS surface code and the XY surface code for bias circuit level noise, and we focus on qubit overheads below threshold. We identify string-like failure mechanisms, which we call fragile boundary errors, in the XY surface code that limit the performance. And we introduce a variant in the XY surface code that mitigates some but not all these error mechanisms. So what is belief matching and belief find? So they combine belief propagation with either minimum weight matching or weighted union find for decoding circuit level noise. And they generalize conceptually similar decoder by Krieger and Ashraf, which instead assume perfect syndrome measurements. It has 3 stages. Firstly, you run belief propagation on the so-called circuit level tanograph, the graphical model describing the circuit level noise. Then use BP to the outputs from belief propagation to set the edge weights in a matching graph, and then decode the matching graph using either minimum weight matching or weighted union find. So what's belief propagation? It's applied to the tanograph of a code, and it has a check node for each parity check and a variable node for each bit. And in each iteration, each node sends its so-called belief to its neighbors in what's like a local application of Bayes' rule. And for each bit, each variable node, BP estimates the marginal probability that it flipped. And it computes the marginals exactly on tree graphs, but approximately, but still quite well on loopy graphs. So what's a circuit level tanograph? It's a tanograph describing the circuit level noise model where you have a check node for each detector, and a detector is just the parity of measurement outcomes that is deterministic if no faults occur. So you can see detector D0 there. There's 2 consecutive measurements in this repetition code circuit, just the parity of those 2, and that will have even parity if no errors occur in the circuit. A variable node in the tanograph is added for each fault mechanism that can occur in the circuit. And then there's an edge from each fault mechanism to the detectors that it flips. So for example, this X error, the red in red, will flip detectors D0 and D1, so there's an edge from that variable node to the detector nodes. As another example, here's a circuit for the XY surface code, and we're imagining a noise model where only one CNOT gate can fail, and it's circled in blue. And every other gate in the circuit acts perfectly, and this gate only fails in one time step, just to make the circuit level tanograph small enough to visualize. So you can see each variable node here is one of the 15 non-trivial 2-qubit Paulis that could occur after that CNOT gate in that time step of the circuit. And then the detectors, which are shown at the top, are the only ones that could fail for some of those different failure mechanisms. And they represent parity consecutive measurements in this circuit. So this is before BP, and you can see the priors at the bottom there, the log likelihood ratios. And you can see that the Z-type errors occur with high probability, so a lower log likelihood ratio, because we're using a biased noise model. Now, after you run BP with this syndrome at the top, shown in red, you can see that the posteriors output by BP correctly identify the ZZ error at the bottom, and it has a very negative, large log likelihood ratio, showing us close to unit probability of having occurred. However, BP on its own doesn't have a threshold for the surface code. There are sort of owing to a problem called degeneracy and split beliefs in BP. So instead, we use these marginals, these posterior marginals output by BP, to set edge weights in a matching graph. So the matching graph just contains edge-like failure mechanisms where each fault flips 2 detectors and no more. So we set the edge weights based upon the hyper-edge failure probabilities and the edge failure probabilities output by BP. And then we can decode this reweighted matching graph either using matching or weighted union find. So how does belief matching perform? Well, we find that it outperforms minimum weight matching and is close to maximum likelihood decoding for L. So we also implement maximum likelihood decoding for circuit level noise for L equals 5 bias circuit level noise. but it's scalable and efficient, unlike maximum likelihood decoding. And we find that it boosts the XY surface code threshold from 0.498% to 0.841% for biased noise, so E2 equals 100. And then for the surface code threshold, it boosts that for circuit level depolarizing noise from 0.82% to 0.94%. And we use stim and pi matching for the simulations. How does belief find perform? So for circuit level this is looking again at circuit level depolarizing noise. We find that it outperforms minimum weight matching, and is 1.42 times higher than just weighted union find alone. But it retains the almost linear time, running time with union find, while outperforming minimum weight matching, which has a much higher degree of polynomial runtime, and is amenable to implementation in hardware. And this will be an updated version of hardware later this week or next. So what about fragile boundary errors? So the advantage of the XY surface code is due to the area-like Z-type logical error I told you about before, Z error on every single data qubit, which means that the minimum weight errors are linear in n for infinite bias. But we show that this high tolerance to the Z errors is fragile at spatial and temporal boundaries. And so we find string-like Z errors that can occur during logical state preparation and measurement, and during lattice surgery, and also at spatial boundaries if a single X or Y error is also present. So here are the fragile temporal boundary errors. So consider a transversal logical X measurement. So we measure every data qubit in the X basis. And then from those measurements, we can infer the X logicals from the measurement data, and we can also infer all of the X stabilizers perfectly from the measurement data. But we no longer have any access to the Y stabilizers. All of these individual X data qubit measurements anti-commute with the Y stabilizer measurements. And as a result, the horizontal string-like Z error just before measurement or during measurements will flip an X logical observable measurement outcome, but be undetectable. So this is a string-like error rather than the area-like error that we were hoping for to have good performance for high bias. And we observe in numerics that these logical state preparation and measurement errors do dominate over logical idle errors for the XY surface code compared to the CSS surface code where the two are comparable. What are fragile spatial boundary errors? Well, these are logical errors that occur at spatial boundaries due to one X or Y error and L-1 Z errors. So it's just you take a Y or an X logical at a boundary and then multiply by the boundary stabilizers, you obtain a Z, almost entirely Z-type string-like error. Again, much smaller than the area-like error we were hoping for. And then we observe in numerics, the scaling below threshold is p to the root n over 2, rather than p to the n over 2, as you might have hoped. For finite bias. So what about the qubit overhead? So we're taking this all together. We want to look at below threshold, what does better, the rectangular surface code or the XY surface code? And we consider this teraquark regime, which is like to estimate the qubit overhead required to achieve 10 to the minus 12 logical error rates below threshold. And what we find is the rectangular CSS surface code, where you've optimized the aspect ratio, outperforms the XY surface code. And so at 0.1% C0 infidelity, the square CSS surface code, so without the aspect ratio optimized, has 1,121 qubits per logical qubit. The XY surface code requires 1,057 qubits, so it's still a big improvement over the square CSS surface code. But the rectangular CSS surface code requires only 681 qubits, and that's because of that aspect ratio optimization. So a partial solution for deforming the boundaries. A partial solution to fixing this fragile spatial boundary errors is to introduce this to deform the boundaries of the code, essentially mapping half of the Z errors onto X or Y errors. And we find that with this deformation, the Z-type logical is still area-like, but it has a reduced weight by a constant factor of 5/9 or a third. But it doesn't fix the fragile temporal boundary errors problem. So in conclusion, we've introduced efficient decoders for handling hyper-edge fault mechanisms in circuit-level noise, which can be sort of more generally useful for wherever you have hyper-edge failure mechanisms in your noise model, which is most experimental noise models. And we show that these lead to significant improvements for surface code thresholds. We identify fragile boundary errors which limit the performance of the XY surface code. We compare the qubit overhead to the CSS and XY surface codes below threshold, and show how fragile spatial boundary errors can be mitigated by deforming the boundaries. But the temporal boundaries remain the problem. So I think in future work, there's still more work to be done to understand how best to optimize to the bias, to tailor to the bias. So there are other variants you can try. For example, neither the XZX nor the subsystem surface codes suffer from these fragility problem that I mentioned. And they've both been shown to have higher circuit level thresholds for bias noise in the surface code. You can also optimize the aspect ratio for both. For the subsystem surface code, you reduce the check weight to 3, which can help with crosstalk. But they both require more qubits for a given distance. So the question is, can they achieve an overhead? So for the XZX, the reason is you have to use an unrotated layout to be able to have the Z-type logicals running along one of the boundaries. So that requires a factor of 2 overhead. And then for the subsystem surface code, a factor of 1.75 because it's a subsystem code. So the question is, can they still achieve an overhead reduction below threshold? And so maybe it could be like this red line at the top here. So maybe it's got a higher threshold, but actually below threshold, the overhead's higher. But hopefully, we could hope that maybe it will have a high threshold, but below threshold, it will also have a lower overhead. And that those numerics have to be done to kind of properly assess which is the best one to use. So thank you, and any questions?
Okay, do we have any questions for our speakers?
One for Joschka. So the main construction where you flip the area using the hypergraph auto. So it looks like if you did that with the surface code, you would wind up with the XZX code. And the decoding problems reduce down to multiple copies of the decoding problem for the codes used initially for repetition codes. Is that property general?
Yes, so yeah, if you take the hypergraph problem, the bias code hypergraph product to classical C codes, then in the infinite bias limits, the performance depends on the performance of that classical C codes. So yeah, the challenge we found and the reason why we eventually started looking at the lifted product was that if you just take any old classical C code, it isn't as good as the repetition code in terms of its block length scaling. So this is why there's a benefit in the lifted product because you get a traction of the head rates and better distance block length scaling.
Any other questions? I've got a question. Oscar, is your decoder available on there?
No, well, time matching it, so the minimum rate matching credit, I'm sure.
Anyone else? In that case, let's thank our speakers again.